plus phi 3 plus phi 4. And that is, and let's go to the right side. We would have the first column, phi 0, phi 0, phi 0, and phi 0. So this is 4 phi 0. Now the second column, we've got plus h and the first derivative of phi against x, minus h and the first derivative phi against x. That vanishes. Now we have the same situation with the first derivative of phi against y. Plus h phi, minus h phi. So the first derivatives vanished. Okay, so we go to the second derivatives. We have 1/2 of h squared multiplied by phi second derivative against x. And the other half. So altogether it is h squared divided by 1, that's h squared, the second derivative against x, and we will have the same situation with the second derivative against y. So let's just rewrite it this way. And we can continue in summing those two equations. We have the same story with the third power of h. Well, there is plus and minus. Plus and minus the same member in the equation, that is h squared divided by 6 multiplied by the third derivative. So this again vanishes. And we have some remains, something that remains in the equation, and that is plus h raised to the fourth power divided by 12, and we will have a sum of fourth derivative of phi against x plus a fourth derivative of phi against y plus, we have described only a part of the series which is infinite. What we have done a lot now. We have some equation. Fortunately, we have cancelled 2 columns in the addition. But still, what does this have in common with our problem? Now I will show you. We want to satisfy a Laplace equation. And a Laplace equation says that the Laplace applied on phi is 0 in a 2D space. It says that, well, I will rewrite it in this notation, phi 2 dots plus phi 2 apostrophes is 0, because the Laplace is a sum of second derivatives against x and y in a 2D case. Okay, so we solve an equation where this is the true. This is here. This must be 0. That's the recommendation of the equation we try to solve. So let's put it 0. And what we have found out, well, it says that a sum of phi 1, 2, 3, and 4 is 4 times phi 0 plus something. Now, we told at the beginning, we make a fine cut of the area with a very short h. We made a number of cuts. that means that h is not very big. Raising a small number to a fourth power makes it much smaller. So if we cut the area with a sufficiently fine cut, we can neglect this piece. And the same story comes with h raised to the sixth power divided by 6 factorial, which is a small number. So this is the biggest remain in the correct result, and by adding h or making h smaller, we can keep this to a sufficiently small amount. So now we have verified that for very small h we can neglect this, and the whole equation only tells us that the potential at the 0 point should be an average of its neighbors, because we have summed those neighbors and it is 4 times phi 0. So that's really the average. Second, we have found out the error. In doing this, we make a small error that is smaller and smaller if we increase the number of cuts or decrease the size of the distance. And that's something that is useful. We can keep the error introduced by the discretization to a level which is acceptable. Yes, it would need a number of cuts, that is, a number of numbers kept in the memory of a computer, but today it costs nothing. Well, then it would need some processing time, but today's computers are fast enough. So that this gives us the possibility to do numerical calculations of electric field or steady current field in geometries where no analytic solutions are at hand. Again, we have used Taylor series to derive expressions for potentials. We have summed that and received a justification for an intuitively derived condition at the beginning that the value of potential here should be the average of its neighbors. So how shall we proceed now? Well, we can proceed in the manner that we cut the area by rectangular grid. Then for any of those values of the potential inside the grid, we can set up an equation. It says left neighbor plus upper neighbor plus right neighbor plus bottom neighbor divided by 4 should be the value. It's one independent linear equation. And we can do it for any point in the grid, so that we will receive a set of linear equations, independent equations, and those equations are of the same amount as the unknown potentials in the grid intersections. So we have a set of linear equations, linear independent equations, that can be solved. Well, that is the easy part of the story. Well, the less easy part of the story is that although we can prove that there must be a solution, we have a problem to achieve a good solution in a reasonable time with sufficient precision. That's something which is a subject to numerical mathematics, but anyway, we will touch the topic in the next lecture. So we are now able to set up a system of equations, but I will also depict a little bit the way of solution of that system in finite time with sufficient precision. That's something we will investigate in our next lecture, which will take place next Tuesday at 8 hours and 20 minutes as to the beginning. So, ladies and gentlemen, your question today, there are no questions at the moment, so please, I will again process the video and put it on YouTube tomorrow so that you will be able to find it. I will send you an invitation for a consultation for Monday evening and another invitation for a lecture on Tuesday. I hope to see you. Shall you have any questions, don't hesitate to ask. And as there are still no questions, it's been a pleasure to lecture for you today. See you next week with a continuation of the method of numerical solution of steady current and electrostatic fields. See you by then.